This is 3.2.2 diffraction grating. Diffraction gratings are a development of Young's double slits. The diffraction gratings will give us a larger distance between the fringes, and that's because the diffraction gratings have many more slits compared to a double slit. So they could be several hundred slits per millimeter. So we can use diffraction gratings to find the wavelength of a laser light. To do this experiment, we need a laser assembly. And a diffraction grating. So when this laser shines some light to the diffraction grating, you have a bright central fringe, and then we'll get several other lines from there. And I'll try to make these equidistant as much as possible. So the central is called the 0th order. Then you've got n equals to 1, n equals to 2, etc. And below that is the same, n equals to 1, n equals to 2. And between the 0th order and the first order, that creates an angle theta. So the equation that relates these together is d sine theta is equal to n lambda. Put a box around that. So d is your distance between slits. Measured in meters. N is the order. Lambda is wavelength in meters, and theta is the angle, which can be in degrees or in radian, whichever you choose to measure it with. Usually it will be in degrees. So you have to make sure that you switch your calculators to degrees when you're working these out. We can also use diffraction gratings to produce line spectra. So if you have certain types of lamps, you can shine the light emitted by those lamps through a diffraction grating. That will create emission spectra that you can then use to determine what those are made of. So let's just write this down. Diffraction gratings can be used to analyze emission spectra to determine the element of types of lights or fluorescing material. Fluorescing material. So in the case of a spectrum, if you had a spectrum, you would have your diffraction grating as usual. Your 0th order would just be white light. Say, for example, the light source you were using was producing some type of white light. But there are different types of white light. So certain wavelengths might be missing. But that doesn't mean we won't perceive that as white. Right? There are different grades of white light. So if it's missing only certain small bands, we could still see that as white light. If you have, for example, just 3 wavelengths of monochromatic red, green, and blue, that could still be perceived as white light, even though several wavelengths are missing. So the 0th order will still give you a central bright white fringe, or the mixed color, so if it's some type of yellow, for example. So you'll see these in light bulbs as well. You have like daylight bulbs. You have cool white bulbs and warm white bulbs, warm being more yellowish, a more sort of warm tone. So you would actually get something like this instead. So this being your n equals to 0, and these being your n equals to 1 spectrum. Now I've done something very simple. This is my spectrum. I've made it have only 3 discrete wavelengths, which is red, green and blue. But you'll normally have a full spectrum there with just a few short bands missing. So you'll see like very small dark bands missing from the spectrum. And so you can analyze those dark bands and figure out what wavelength was supposed to be there that isn't there. And if you figure out what wavelength was supposed to be there but isn't there, you can pick out the wavelengths that are missing. And if you know the wavelengths that are missing, you can compare that to different materials and figure out what materials are made out of. So for example, we can look at sunlight and we can determine what the sun's made of. And that's how we know that the sun has got isotopes of hydrogen and helium mainly, which are emitting light. Okay, start a new page. We'll do a couple of examples. So if D is equal to 2.5 times 10 to the minus 6 meters, how many slits are there per millimeter? You can pause the video here to try the question. You can play the video when you're ready to see the answer. So first let's consider what this looks like. If you have 2 slits and the spacing between them is 2.5 times 10 to the minus 6 meters, that means that per spacing you have got 2 slits. If we add a second spacing, we end up with 3 slits. If we add another spacing, so we get 3 spacings, we end up with 4 slits. So in other words, the number of slits is always 1 more than the number of spacings. For very, very large number of slits, we can assume that the number of slits is roughly equal to the number of spacings. And that's what we're going to do in this case, because we're going to get very many slits. So the slit spacing is equal to 1 millimeter all over the number of slits. So we rearrange this to get n equals to 1 times 10 to the minus 3 over the slit spacing. We'll put our values in. And that gives us about 400. Now we actually know that there's 1 extra slit on the end, so that should be what? 401. But 400 is roughly equal to 401. So we'll just round it to 400. So we can say that n is equal to 400 slits per millimeter. Let's do another example. So for red emitted by cadmium, lambda equals to 6.3 times 10 to the minus 7 meters. So if I draw a diffraction grating, I'll just change that back to black. So here's our diffraction grating. Our first order and this diffraction grating had D equals to 3.3 times 10 to the minus 6 meters. So the question is, what is the angle between the first and second order spectra? Pause the video here to attempt the question and play the video to see the working out. So to work out this question, we want to first sketch the maxima. So ultimately what we want is we want the angle between the second and first order, so I'll call that theta 2,1. Now to get theta 2,1, we need to work out two other angles. First, we'll work out theta 2, which is this large one here, which is the angle to the second order, and the angle to the first order, which we'll call theta 1. So what we need to do is we need to do theta 2 minus theta 1, and that will give us theta 2,1. So first I want to rearrange the equation to work out theta. So we'll do d sine theta equals to n lambda. That implies that sine theta is equal to n lambda over d. So theta is equal to the inverse sine of n lambda over d. So theta 2,1 is equal to inverse sine of 2 times lambda, and lambda was 6.3 times 10 to the minus 7. All over d. Which is 3.3 times 10 to the minus 6. And then we take away the angle for the first order, which is inverse sine of 6.3 times 10 to the minus 7. Here n is equal to 1, hence why I haven't got 1 times. All over 3.3 times 10 to the minus 6. So you put that into your calculator, you get an angle theta 2,1 is equal to 11 degrees. And that's the end of 3.2.2.